Hello and welcome everyone to another session in the Data Hour series. We are thrilled to have you here for this session full of action-packed learning. I am Priyanka and I have my associate Deep who will be helping you with any queries or issues that you have in the chat section. He'll be posting the important links in the chat section, so please do keep an eye on it. My name is Priyanka. I am a part of the data science team at Analytics Vidhya, and I'll be the moderator for this session. For those who have joined us for the first time, a brief introduction of Data Hour session. The Data Hour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour to dedicated to data. So we are hopeful that these sessions are going to be a great source of enrichment and value adding to our community members. Now, on to our session today, which is quantum computing simulators acceleration. Quantum computing aspires to deliver more powerful computation and faster results for certain types of classically interactable problems. Circuit simulation is essential to understand quantum computation and the development of quantum algorithm. In this data hour, the acceleration of quantum computing simulators using NVIDIA GPUs and QODA will be discussed in detail. I hope you are excited to attend the data hour with us. And before we kick things off and I hand it over to our speaker, a quick recap of the housekeeping items. We are recording the sessions and we will make the recording available in a few days on our YouTube channel. Please use the Q&A section for asking any questions you might have during the session, and we will do our best to answer them as the data hour progresses or towards the end. Also, we will share a poll about feedback towards the end of the session, which I request you all to kindly fill up. Now, on to our speaker in this session of Data Hour, we have Dr. Manish Madani with us. Dr. Manish has 17 plus years of industry experience in high performance computing and weather. He has ported, benchmarked, and optimized HPC applications from various domains, including weather, insurance, agriculture, disaster management, molecular dynamics, etc. His work is patented and published in various peer reviewed research journals. Dr. Manish has worked in Cray for 2 years and in IBM for 10 years. During his PhD from Center of Atmospheric Sciences, Indian Institute of Technology, Delhi, Dr. Manish has developed air pollution models for the dispersion of air pollutants in low wind conditions. Presently, Dr. Manish is working as a principal solution architect in HPC, AI for HPC, and quantum computing simulations at NVIDIA. Over to you, Dr. Manish.
Hi, good evening. Am I audible?
Yes, sir, you are.
Yeah, thank you. May I share my screen?
Yes, you will be able to.
Okay. I think my screen is visible.
It is, sir.
Great. So let me start with one video and then we can start interacting. This video is on me, so just would like to start with that and let everyone settling down and then we will start discussing. Is it audible?
Yes, sir, it is.
ये लो खाना।
अरे चाची, इतना सारा खाना, पर आपके हाथ का अचार गायब।
धूप निकलेगी तभी तो अचार तैयार होगा। भगवान जाने इस मौसम का, बार बार छत पे भागते रहो, एक यही काम रह गया है मेरा।
आपके घुटने कैसे हैं चाची?
अगर ऐसा मौसम रहा ना तो एक दिन ये भी खत्म हो जाएंगे।
मेरे पास एक इलाज है चाची, ये देखो।
फोन पे?
हाँ, धूप कब निकलेगी मतलब आम कब सुखाने हैं। सर्दी कब पड़ेगी, मतलब घुटने कब बचाने हैं, ये सब आपके फ़ोन पे।
ये सब तुम्हें कैसे पता है?
मेरी कंपनी है ना, उसका ऐप है ये। मौसम से हम सबको फ़र्क पड़ता है चाची। पता हो मौसम कब बदलेगा तो हम कई चीज़ों की तैयारी कर सकते हैं, आपके अचार की भी।
अरे वाह, तू तो कमाल का वेदरमैन निकला।
Weather is a hidden layer of insight that can predict how we feel and the decisions we make, the foods we crave, and how and where we satisfy our appetite. We drink more fizzy drinks when it rains and eat more yogurt when it's windy. Indoor paint sales increase when there is above the average wind. Hand and body lotion sales increase when there is no cloud coverage. Auto gas sales spike when temperatures are colder than average. Arthritis and COPD can increase on specific days. You can get an
So, hi everyone. Good evening. Once again, welcome. Once again, thanks to team to giving me opportunity to discuss here my learnings. The video I shown here is picturized on me in my previous assignment. It is still valid, but one of the objective to show the video is that I can act also. So that was one of the objective, but having said that, that is related to my previous assignment where I was the country lead for in the weather company, IBM. IBM acquired that company. You might have heard the weather channel. So there I was the country lead, technical lead for the same. And then we used to predict the weather for with every 15 minutes update. And that 15 minutes update at very high resolution was possible because we were using the accelerated computing to run the weather models, right? So the accelerated computing helped there. What I say, accelerated computing or NVIDIA GPU that helped to have quick update in the weather forecast as well as for higher resolution, right? So, it is much better resolution than what we have right now at country level, what model we run. But so that way it was relevant, and there these video were shoot. So I thought just to start with that to show that I can act also. So with that, I would like to start. So just a brief background about me. I am a applied mathematics postgraduate. Then I get chance to do PhD in IIT Delhi, and I worked mainly in IBM for 10 years. There I was in various departments. I was 3 years in UK, and then I was leading various groups in IBM. Recently, last 2 years, I am in NVIDIA, where my key role is to accelerate the applications, HPC, AI, or AI for HPC. So to accelerate them, to share the best practices, how to run the applications, and how to get the best performance on the given system, right? And as well as recently, I picked up this quantum also, which is recently new development in the NVIDIA, where we came up with quantum and QODA quite. So that we will discuss in this session, right? Before going deeper into that, whatever we will discuss today, there are few slides which I prepared and few I took from internet. I try to give the reference those to give some background on that. With that, more important thing is whatever today I'm presenting, you will get more detail in NVIDIA GTC. That is our annual conference, 2 times in a year. So just now it is coming September 19 to 22. The registration link is we will share in the chat, or it is given on my slide also. Here, I request you to register. It's a free, and then you can go in sessions. You will find relevant session to your interest and domain, and those are very interesting for you, right? So you can look for any segment, industry-wise segment, primary topics. Say we started with data analytics. Certainly you will find here for quantum also, but you can see for data analytics, and you will find there's so many talks here. So you can add those schedule. You can look into your India time later on, or you can look live also when those were going on, right? So this is one of the key. You should try register and try to join there and look for those your relevant discussion, right? Let's come back. So today in talk, first I would like to talk about accelerated computing, what it is and what it means and how we do. Then I would like to cover few basics of quantum computing, though I am also learning in this domain, but whatever I could gather, I would like to share. There would like to share quantum computing versus classical computing, like what our minds share and how we think and how it is different. Then would like to talk about quantum computing simulators, what's the need and what it is doing. There are quite a number of simulators are available, and what NVIDIA is doing in, and I will discuss in that domain, that we came up with the accelerated, platform, QQuantum and QODA, where we get the accelerated performance of these quantum computing simulators or frameworks, right, using NVIDIA ecosystem, right? So with that, let's start, and first would like to discuss about accelerated computing. You might be knowing, many of you, but a few slides on that. I was told that all audience are from various backgrounds, so I try to cover almost all the domains what we see in our college or in our day-to-day work. Almost all the domains are covered here. We have accelerated computing in all the domains, right? Right now, if you see, the expectation is day by day we are having more simulations in all the domains, I mean all the codes, and we do have models that we expect to run faster. We need quicker results with more physics into it, more higher resolution, with lesser time steps, or we would like to go more to understand the phenomena more and with more accuracy, right? So that's where we have, and then we would like to utilize nowadays with the availability of more data, more observations, we would like to utilize those. So that's where now what we were doing with the traditional computing, and now we would like to accelerate those. So to accelerate those, nowadays the GPUs are being used as a co-processor to the system, and that's where we are getting faster and faster results of the given simulation or given models. That could be range from end to end. Even recently, COVID drug, what we get, COVID vaccination, that was also possible because we have quicker simulations on these accelerated system, right? We can go in the protein folding, drug design, we can look for crash simulation, we can look for weather. Nowadays, you see even in India, particularly last 20 years, the significant improvement that we used to have, say, cyclone or any disaster or extreme weather events, there we used to have life loss. And now if you see, timely early warnings are being given, all are being evacuated, and we have very minimal or negligible life losses, right? So that is, again, that is possible using high performance computing and accelerated computing, right? So the applications are enormous. They are in every field. So everywhere the accelerated computing being used. What it is, I will come on that, right? Just now I'm sharing the use. Similarly, that was for the HPC side. But if you look now for AI side, where we would like to have personalized marketing, like we go on Google look our interest, and accordingly we see the advertisements. Similarly on Amazon and other places, we need to have personalized requirement, and accordingly those are being addressed. And that is possible through AI as well as AI ML, all these things. So there also the expectations are growing fast to have faster results and accurate results, right? It's not that only we are seeing in our day-to-day behavior. If you see the number of research papers published in the last 10 years, there is a significant growth in the DL, deep learning based, as well as HPC. Both are being growing. And one of the reasons for growth is the availability of data, computational power. Even COVID time, 2 years, there's significant paper were published because their data was available. Johns Hopkins University maintained the repository and the computational power was there, right? And with that, everyone was able to do the simulation and publish the paper. And that is growing across the domain. So that's where the deep learning frameworks like transformer, convolutional network and all, they are able to run faster. And that's where now we have more research into that direction, right? Okay, so let's go a little back how the accelerated computing is started. So earlier from 1990 onwards, there used to be every year the CPU frequency used to increase significantly, right? Every year we used to see some say 1.5x increase in the CPU. That's where all the application automatically get the speed up. And that time we were getting a speed up, meeting the expectation that we need to have early results, and that it was going on. Around 2005, we realized that we can't go for more speed up because it is there is a limitation in the say energy requirement, and then the chip size. Both were having the limitation. So that's where the growth in the CPU speed up was negligible, kind of 1.1x every year, right? The NVIDIA started in 1993 as a graphics company. Their cards were used for graphics mainly. Around 2005, that time onward, around that time, they came up with the QODA framework, which were able to exploit the which were able to do the number crunching on this graphics card through QODA, right? And that's where they start being used as a co-processor with the CPU. And that's where we are seeing now again performance gains significantly, like more than 1.5x per year with the GPUs. And it's a mix of hardware innovation as well as ecosystem being developed. New softwares are coming, new algorithms are coming, and we are seeing continuous speed up in this direction. And we are expecting 1,000 times speed up by 2025, right? So that's where GPUs start coming into picture. One more example, every year, 2 times in a year, the worldwide top 10 systems are being defined, right? So if you see, I just put a list of top 10 system and then top green system, which are energy saving or economic in terms of energy. If you see the co-processor or GPU being used in top 10 system, out of top 10, almost 8 system have the co-processor, 8 or 7 has the co-processor. And if you see energy side, all 10 has the GPUs. So they are good for energy saving, they get the more speed up, and that's where the uses are increasing because they are easier to use day by day. More algorithms are being developed, more applications are being ported. So that's where the uses are increasing, right? So we almost knowingly, unknowingly, we are using the accelerated computing in our day-to-day life. How it works? The GPUs are dedicated processor. They are good for single instruction, multiple data. So what happens, any application we take on CPU, there generally we start our application, read the input, read the data, whatever required, read the input data. Then we do the compute intensive loops, they are there, right? We do the number crunching. And after that, we would like to have results in the desired format. So we do the post-processing and then write the results back into our files or database or wherever. So only the compute intensive part, which is there in the application, maybe that is 5%, maybe 20%. If we offload that part only on GPU, we get significant speed up in the application, right? That speed up can vary from 10x to 100x. That's what we are seeing in our day-to-day work. So if we identify the compute intensive part and that only we offload on GPU to have the processing faster, and that gives a significant speed up in the application. And that's how we say the CPU works. With CPU, the GPUs are there as a co-processor, dedicated processor for particular type of computation like single instruction, multiple data, any loop, which we call it as a kernel, while offloading to GPU. So if we offload that, that becomes very faster because the GPU chip has many, many cores. It may have up to 6,000, 7,000 cores. So they work together and it is faster. So parallel instructions are faster. and we get significant speed up, right? 3 ways to accelerate the applications. Generally, we have built-in libraries. One can use those. Compile time, one can link those, and very minimal modification required in the code just to initialize the data and so on. So that we have like QFFT on random number generation or maximum at QBLAS, whatever library we are using in our day-to-day purpose, all are being accelerated. One can use them easily, right? We call it as a drop-in acceleration. The second way to accelerate application is OpenACC directives. These are pragma-based. So we need to define which portion of the code has to be accelerated. With pragma, we define that this loop has to be accelerated. Then we transfer the arrays from CPU to GPU, and then we do the computation, right? And third one, which is the programming language, where we use CUDA C or CUDA Fortran to accelerate the application, which gives us maximum flexibility in terms of which portion of the code to be offloaded on GPU, then how many threads, how many grids to be assigned for those GPU to run that particular kernel, right? So it gives all the flexibility. So the CUDA is being, but the left to right, it takes the time, right? The libraries, calling libraries is much easier. OpenACC is mediocre, and CUDA conversion to CUDA is taking a little longer, right? But most of the application now, if you see, they are already accelerated on GPU. If you have any application you are working, you want to use GPU, just go on NVIDIA web page. There you check, you may find that already that application is accelerated. You can use for your day-to-day purpose, right? So that is the accelerated computing that is being used in every domain, be it AI, ML, DL, whatever you say, or HPC. Everywhere it is being used. So now would like to discuss about quantum computing, and then how the accelerated computing being used in quantum computing, right? Since quantum computing is relatively new domain or new computing era, would like to explain that what it is by a game, right? So in this, like we are playing with computer, a game like solitaire, what we play. So here just we are, and this I took from a TED talk. There they explain this way. So I like this, and I'm trying to show here. So generally how it goes is we spin a coin, and then we start with the head. Then we spin the coin, the computer spin the coin, and then we can't see what is there on the coin. It's a dark. Then again, first computer play, then we play, we again spin the coin. Then again computer spin the coin. And finally, if head comes, then computer wins. If tail comes, then a user or we win, right? That's how the game is. It's a simple, like we need to, we need to toss the coin, and then first computer does, then we do, then again computer do. And then if in end head comes, then computer wins. If tail comes, then we win, right? So this has been tried and tested, almost equal chance and equal wins between player and computer, right? So that's a fair thing, and that's how it goes. Now, before coming to this game further and explaining quantum computing, little bit theory on this, and I won't go much deeper into that. But what happens earlier, physicists figured out that first they figure out light is made of particles, and then there was a Nobel Prize for Einstein. Later on, another scientist, Thomas, and then de Broglie, they figured out that light is also exhibit the wave-like behavior. So a particle can, or a light can be made up of particles as well as waves, both, right? So their duality is there, wave-particle duality is there. There are two kind of properties are there in the, and it exists now. So now means it is believed that it is there. So now what we feel is, if we observe, then a particular, what we say, the smallest quantity is quanta. So that behaves as a particle if we observe. Otherwise, it propagates like a wave. The properties are like wave. So there is a duality in the features of any given particle, right? So the quantum computer, they are built on this property. So they represent both the properties of particle or quanta, that one particle can be in two states at a time, right? If we observe, then it is a particle, otherwise it represents the wave-like function. Right? So with that, the quantum computers start building. Google and IBM are building, they are leading, but there are many other players are there. The objective here to say is they are totally different mechanism to have the quantum computing than what we think in terms of classical computing. A simple example is we have a candle and we have a bulb. Whatever we do candle, n number of candles, whatever big candle is, whatever we do, but the candle can't compete with the bulb, right? And both have different technology behind and different way of innovations and so on. So that's where the quantum computing is different than classical computing. Still, since we are using classical computing so long, we would like to see how it is different than from the quantum computing is different than classical computing, right? So coming back to this game, and now if the quantum computer plays this game against the user, you see almost every time quantum computing is winning the game, right? And why it is? So before that, we have the classical computer. There we have the bit, which represent only one state at a time, either 0 or 1. We can classify it as a 0 means head and 1 means tail. So we can say that either head or tail. In classical computer, we used to get only one of that. Whereas quantum computer, they have the non-binary fluid identity. They can be in a state, in between they can be in dual state. So half yellow, half blue, if you are seeing in the screen. And when we want to see the end result, they can lead to that situation according to the probability or whatever desired result we need. Accordingly, they change their final state, right? So what happens in this game? First computer plays this, and then it remain in the dual state, both head and tail, both it keeps. Then we play, flip the same coin. Again, it remain in the same state, both the state. Finally, computer, what it does is, it knows that head wins. So that's where it come back to the head situation. And almost every time we get the head in the coin, and that's where the computer wins, right? So it's just a representation trying to represent what it is mean by quantum computing or qubit, right? How it represent. This is a through game we try to represent, but if you see again, what we would like to show is, and here I would like to discuss two key features of quantum computing: superposition and entanglement. So what happens is, if we see the bit, either we get 0 or 1, and generally we say that 100% we are sure with it will be either 0 or 1, and that's how we go with the classical computer, right? Whereas in the qubit, we have probability. It can be 0, it can be 1. We can have equal probability for 0 or 1, 50%, 50%, or we can say it could be 30-70 ratio or 80-20 ratio. Anything could be possible. And that's where we call it in qubit, two states can be represented at a time. And we call it as a superposition of a state. So two states in a qubit can be represented, and we call it as a superposition inside qubit, right? Now, that is one feature of the key feature of the quantum computing, that we have superposition of two states inside one qubit, right? Now we see how it goes when, and there is another feature is, when we go more than one qubit, they are entangled with each other, right? So suppose we have two qubits, and when we entangle those two qubits, then it represents the 4 state of the, 4 quantum state at a time. So 2 qubit, each qubit may have say 50%, 50% and 50%, 50%. As I am taking an example of 50 only, but it can be 20, 40, 60, 80, whatever it is. So if you see 2 arrows are going up in the first qubit and 2 arrows are going down, but finally with entanglement, these become a 1 state of a quantum computing. So these are entangled with each other, and that's where we could represent the 4 state in 2 qubit. And that's where it goes with the 2 raised to power n. So number of qubits, whatever we have, there the number of states what we can represent is 2 raised to power n. So that's the difference come. If we take bit, single bit represent 1 state, whereas 1 qubit represent 2 quantum state, and when we go more than 1 qubit, 2 raised to power n, those number of states we can represent, right? And that's where we are talk more that if we can represent more state in one simulation, that way the simulation become faster. And that's where we are looking for more qubit as we go for with the quantum computer, right? So there are many quantum computers are there now, and they are coming up. You may hear that IBM is also offering free access to the quantum computer with the limited qubits, and there are more are coming, more are the expectations there. But there are some challenges with the quantum computers. They are evolving. There as we say, the quantum state is fragile. So the fabrication must be precise. And they generally qubits operate on very low temperature, that is around minus 200 degrees centigrade. We need to maintain a particular state of qubit to have same state while we are doing the computation, right? There is a verification is also sometimes challenged because we can't measure the complete state so precisely. It's a verification is becoming difficult with that, right? Similarly, architecture, there are more errors occur when we do the computation than classical computing. Those errors come from the different gates, and I'm not going in that deeper into that gate side, but the error propagates as we go more further and further. That's where the error is also one key factor, how to control the error, right? The existing quantum computer, they are limit in scale because, as I said, all 3 reasons before. Sometimes there is an error also, more error propagate, and speed is also what we expect. Right now, there are some limitations on the speed also, right? So this is where the actual quantum computers are. But at the same time, the researcher would like to continuously work on development on the algorithm, because we all know quantum computers are becoming reality. If not now, in next couple of years or maximum a decade, we will have quantum computer which will solve those problems which we are not able to solve with classical computer due to some limitation. Again, I would like to say whatever we run on quantum computer, same thing can be run on classical computer. But as I shown that at a time, 1 state will go in the classical computer, whereas in quantum, many states can go together. So speed is also a key. And because of those, right now, we are not able to solve many problems, which those unsolved problems should be able to solve with quantum computer. That's the expectation, right? So so the key areas with the quantum computer, what we are looking forward right now, though it will be applied in every domain, including disaster management, including like anything what we look for. But right now, the key focus more is on finance, the quantum chemistry, the cryptography, and route optimization. These are the 4 domains. You will see the more work there. Other fields are also picking up, but there is a more focus on these things, right? Then what is the expectation? If you see the next chart, what we are looking for, number of qubits, they are significantly higher over the years. Then we look for fault tolerant computing, speed up threshold, and all which will show the advantage of quantum computer, right? It should show some advantage, otherwise why we will look for quantum computer? We are okay with the classical computer as well, right? So these are the expectation over the years. We should have, say, around 1000 qubit by 2025 and 10,000 by 2030 and so on. Those many qubits we need, that should be fault tolerant, and then we should see the quantum advantage with that, right? So those things are going on right now. The work is going on towards the quantum computer to have with those qubits. But then with that, there is a need and there is an advantage to have quantum simulators, right? Simulator is same as what we do if any car manufacturing company, they first simulate the car inside their office or whatever you say. They try to simulate it, see the design, how it will look like, what will be the safety feature and all. First they simulate and then they go for actual production, right? So here also what we are looking for is, or not looking for, what we have is, now we have quantum simulators. They run on classical computer, but they behave as if they are running on quantum computers. And those are helping in many things, like having the new quantum computer, new hardware design, algorithm validation, error propagation control, and so on. So these simulators are run on classical computer, but helping in all segments of quantum computers, right? And they are easier to use because they can be run on classical computer, right? So now slowly I am coming towards the GPU side of a story, accelerated quantum computing side. I think I'm doing okay with time. So what happens is, on classical computer, we have CPU plus GPU, which accelerate any applications. Now what we are looking for is, all the simulators, they are from Google, they are from IBM. I will go through those. So these simulators, what we look for is to simulate the, say, first question is, what new algorithm can be developed by simulating thousands of qubits? Those kind of questions we would like to try to address. Or what use cases can this value provide value to, right? And we would like to have quick simulation on this or accelerated simulation. That's where we have QQuantum platform, which runs on NVIDIA GPU, which accelerate all these frameworks like Circ or any other framework you say, those are being accelerated. I will come on that. The right side, what I am showing is NVIDIA QODA. So this is quantum optimized device architecture. So what we are envisioning, or the quantum community is envisioning, is we will have quantum computer, but for a given application, the application will run in hybrid mode. The part of the application will run on quantum, remaining will run on classical computing, right? And to have seamless transition between classical and quantum computing, we came up with a platform, or NVIDIA launched recently. The platform is QODA, Quantum Optimized Device Architecture, right? So let's discuss one by one these. Before that, just to share the few algorithms which are more common and very commonly being used inside the quantum computing. Two of them are Shor's and Grover's algorithm. Shor is prime number of factorization for encryption. So any number which can be factorized into the prime number, say 2 prime number, and like say number 6, which can be factorized into 2 prime numbers, say 2 or 3. So those things can be used. So that's where the Shor algorithm comes into picture. Those are also ported that uses the quantum Fourier transform, and those are ported on simulators that is available. Similarly, the Grover's algorithm, which is for unstructured search, that gives the quadratic speed up using the quantum simulators. Similarly, the Shor algorithm gives the exponential speed up over the classical computing, right? Just would like to discuss these areas, won't go much into detail. These are being evolved. The quantum is now being used in machine learning also, where we have the quantum generative models. Those are being used, right? So QML is also very popular now. There are various segments like classical data and using quantum machine learning, or quantum data with quantum machine learning. There are various things being explored, but you will find relevant research papers in that. Similarly, for quantum chemistry, there is a variational quantum eigensolver. This is being used, and they are being used for protein folding and other things. So this is also one of the near-term domain where you will see the application of quantum is more. And the last but not least is the route optimization or resource optimization, resource allocation. That is a common problem. So here also you will see more usage of quantum computing, right? So let's talk about QQuantum first, and then we will talk about QODA, and then happy to have questions on that. So QQuantum Appliance is a fully contained software solution which enable the highest performance of quantum circuit. These are available in the containerized form. They can be easily downloaded and easily installed on GPU system. And with that, you can see the performance with all the existing frameworks and algorithms, right? How the structure looks like, we have two algorithms accelerated inside QQuantum, Q-state vector and Q-TensorNet. Both are accelerated. Then we have the Circ, which is a common framework, and with that you will experience the accelerated performance. Right? It is a platform, as I mentioned, that it simulates ideal or noisy qubits, enable algorithm research with a scale and performance not possible on quantum hardware or simulators today, which are CPU based, right? So on GPU based, we get the faster as well as we get more depth. We get few more qubits, which are not possible on CPU. Right? So the frameworks like Circ, Quicksit, and Penylane, most commonly used, these are available on QQuantum, and they are C and Python APIs. And one can go and download from developer.nvidia.com/QQuantum. Right? And just to say that we accelerated these frameworks, right? So one who is using these frameworks, they can continuously use those. Inside the QQuantum, these frameworks are accelerated and one can get the speed up, right? So full quantum simulation stack with the Circ and QSIM front end. Then we get the performance, significant performance gain. So say the Circ and for these algorithms, I'm not sure bottom you could see. So here the right side chart, it shows for 3 algorithms how the speed up looks like. Shor algorithm, and for QFT, Fourier transform, and supremacy. That all 3 algorithms we are showing the speed up. These right now we are showing for single node when we use 8 GPU, and you see the speed up relative to the CPU only run for the same algorithm, right? So we took this same algorithm, run only on CPU, then we run with GPU, and we get, say, 1 GPU almost 10x speed up, for 2 20x, and so on. For 8 GPU, we get around in between 65 to 80x speed up, right? So this gives the significant speed up. Similarly, the range of use cases, various things have been tried with this QQuantum, even Amazon Bracket, Penylane, Pascal, and other frameworks. And you are seeing that depth is also 24x more depth. We could go with this QQuantum and we get the better speed up, right? Similarly, the TensorNet, which gives significant speed up, and so from for many practical quantum circuits, tensor networks are required, which gives simulation to 100 to thousands qubit. Earlier with all 3 algorithms, we have 32 or around 30 qubits, what we can go so far. But here with TensorNet, we can go up to thousands qubit. And cuTensorNet provide APIs to convert the circuit in Circ or Qiskit to a tensor network, and then calculate an optimal path for the contraction. And then finally, we get execution plan and execute the tensor network contraction, right? I'm not going into detail, but all details are available in the slide, so one can look into that. And there are related research papers are also available. The references are given. There are many research are being published on this with the tensor networks. But if you see the speed up, in this, I would like to show the speed up, and they run on the our NVIDIA Selene supercomputer, which is the fastest supercomputer. And there, if you see the speed up, vertex count, and supercomputer with 93% accuracy, we get up to 10,000 vertex problem we could solve with 5,000 qubits, right? That is the power of accelerated computing. So where we are in terms of right now is state vector and tensor networks. So with tensor network, we could run around 32,000 qubits. And with the state vector, we are around 32 qubits roughly, right? With all these algorithms, state vector, VQE or Shor algorithm and QFT. So that's where it is. But with GPU, we are getting significant speed up, and that is giving advantage now. So any framework one is using, one can find their acceleration on GPU using cuQuantum, and that is easy to run and easy to gain the speed up, right? And there is no compromise in terms of accuracy and all. Now I would like to come towards QODA. So as I mentioned before, future will be hybrid, where any application, part of application, say pre-processing or co-processing or post-processing. So in that, only the co-processor will go, quantum algorithms will only be offloaded on quantum computer. Pre-processing, post-processing, they will remain on classical computer, right? And then in classical computer also, we can have CPU and GPU. That's where we came up with the QODA, quantum optimized device architecture, that gives this hybrid computing platform. One can easily use that and easily offload between classical and quantum. Right now, everything goes on classical mainly because quantum computers are there, but they are limited in access and for limited people. But it can be used. We are in partnering with all the hardware providers. There the QODA is being ported. And if the quantum computer is not there, even on classical computer, we can use the classical supercomputer as well as quantum circuit simulator, and we can use the same QODA. So tomorrow, when we have the access to the quantum computer, no need to change much. Same QODA will allow you to run your application on quantum computer. And that's where we have seen this in hybrid algorithm. We have seen the performance gain for VQE, iteration speed up for this hydrogen chain, where we are seeing when we increase the number of qubits, the speed up is also increasing significantly, right? We are going up to with 20 qubits, we get the speed up to say 287x, right? And this is in comparison to the class. If we have everything only on classical computer and how it works, that is the comparison. With that, I would like to say QODA is the development platform. So now what NVIDIA has, one is cuQuantum Appliance, where one can see the quantum simulator framework and their acceleration on classical computers with GPU, significant acceleration with control in the error. And then QODA is for pioneer quantum applications. And there we are working with in pharma, energy, and machine learning and more domains. They are upcoming domains, right? I guess this is the slide where we are showing that what are the frameworks already accelerated using GPU. Here you will see left side, Circ, Qiskit, Penny Lane, AWS Bracket, and all other frameworks are there. Similarly, where we are working, almost all the world's HPC centers, there we are working now and implementing these. And then other power users whom we are collaborating is IBM, Google, and you name it, we have it like that, right? So with that, this might be one of my last page where I'm sharing the resources. Everything what I discuss openly available. One can look on Google and they will find these links. There are many blogs, many details, but everything is open source. One can download and one can start using it, right? So with that, I would like to thanks again and happy to take questions.
Thank you so much, sir. So, sir, before we start with the question answer section, um, so there will be a feedback poll before we proceed ahead with Q&A. I would like you all to, start filling in the feedback poll. It will really help us to conduct more such sessions. And yes, so we will take the Q&A as well. So you will be able to find the Q&A section at the bottom of the screen. If you want, I can read the questions to you.
No, I guess I can take it up. And once
Thank
again, I try to cover maybe little more, so might be little faster. Apology for the same, but happy to have answer to the questions and happy to connect later on if you have any questions, right?
Thank you so much.
First question, certificate bhi milega. Sorry, I could not get that. So I ignored that question. Not sure what.
In regards with the NVIDIA program that you told us about in the very beginning.
Oh, GTC. Okay, if you attend the GTC, there are session attending, there is no certification, but there are some DLIs. We conduct the DLIs, which is for a day, 8-9 hours. Few of them are free for AI. You will find there for quantum also, one DLI is there. Those are free. In few of the DLIs, we give the certificate, and few are only for say 2 hours, then we do not give. So that certificate is valuable. One can use in their wherever required. Yes. But otherwise, attending GTC, that is a conference and virtual, so no certification. Is there any reason why you guys do not use TPU? So TPU is not from NVIDIA, they are from Google. So we have our QODA cores, so we use those more, right? Non-binary fluid. As Abhishek, I try to explain. In classical computing, we have either 0 or 1 in qubit. So we have defined state, right? So say we take example of weather again. We generally say barish hogi, nahi hogi. It may rain or it may not rain. But nowadays we talk about 80% chance of rain. That's how we are getting the forecast, right? So this percentage thing is non-binary fluid kind of, that where we are defining the percentage, we are going in between the state. We are not talking hogi, it may rain or may not rain. We are going beyond that. We are saying 50% chance of rain, 80% chance of rain. So that is kind of a state where it's a non-binary fluid. Yeah. Classical computer that headwinds, then it will simple win. Not how a quantum computer is different, how you interpret the accuracy while comparing both quantum. So one thing is this example, what I shown the game is just to explain how quantum computer works. End of the day, even if you change the head or tail to the classical end user, last one chance is given to the computer, right? And he knows what it will win. So he will flip that side. That's what I try to convey. It's not that defining head to computer, that's where it is winning. If you say the last is tail is winning, till last moment it has both the state, head or tail, both he can take. And accordingly, whatever rule we define in our program or whatever we do, that side it get more weight and it take that state. So that's where it works, right? Hope I try to clarify. And how do you interpret accuracy while comparing with both quantum computer and classical computer? That is That is, accuracy is a challenge now. That's where we are working, because the gates are different in classical computer and quantum computer. The gates what we are using in quantum computer, their error is propagating. So significant work is going on towards accuracy, minimize the error. So that work is going on, right? Eric, yeah, you are right. Every time quantum computing is not always needed. That's right. Even that is true for everything. Like start from your calculator. For 2 + 2, you need calculator. You do not need computer to write a program and add those. Though you can do that through programming. Similar way, a program can run on classical computer. Does not need to have quantum computer. The quantum computer, classical computer will remain there in future. Again, that will be there. The application which can run on classical computer, they will remain on classical computer. Few unseen the phenomena of nature or in our body, like how brain works, how protein folding works. Those things we could not simulate now with the classical computer. That will be simulated through quantum computers, right? Brijesh, in a traditional way, we can represent a switch as close to represent 1 and open represent 0. In qubits, the same thing will be there. You can define 0 or 1. That will be there because you will define either 0 or 1. But if you would like to define in between states, say 60% chance of 0, 40% chance of 1, those can also be defined in qubits. So that's the difference. In bits, either it will be 0 or 1. In qubits, we can have 2 states which can have 0 or 1 together. Or if we would like to go in between, like 40% chance of 0, 60% of 1, that can be defined in the qubits, right? I think, Abhishek, I tried to explain a little more, but let me admit, this is a different, as I try to give example, candle versus bulb. This is different thought process, different thinking in this, how to look for quantum computing, right? And that's where we should think differently for quantum computer. I try to give some examples, some analogy, but still it may take it takes little time to think towards the qubits and how it works, right? Is there any problem that could be solved by classical computer machine can't be solved by using quantum computing? Is there any that could be solved by classical? No, it can be solved, and it's a vice versa as well. One thing is clear, whatever we are solving on classical computer, that can be solved on quantum computer, except waste of resources. That is one thing, but we can have 0 or 1 state in qubits, and we can solve that problem, right? It should be faster depending on the algorithm, but we can solve. Other way around also, you will see the literature. Any problem what we are solving on quantum computer, that can also be solved on classical computer. But on classical computer, it may take too much time. It may not represent all the states as we want or as the natural phenomena is. That's where the challenge will come. But whatever we will solve on quantum computer, that could be solved on classical computer and vice versa, right? I think, Sharon, I try to answer your question. Then right now we can, can we start research in quantum computing? Yes, already there are many researches there. Many research papers are available. You can start research in quantum computing. C-lang works mostly with 1 or 0. How does state represented in C? So you're talking about programming now, how to represent that and all. There are examples available of programming. You will get better idea once you download those and get a feeling, right? When will be normal quantum computer be available for the normal person or personal use? Quantum computers are available now. That's not a problem. What I heard, IBM's 127 qubits is available. Same Google is also coming up. But for personal use and all, it may take some time, 5 to 10 years. That's where I feel. Quantum computing will be able to solve accurately weather prediction. Accurately weather prediction, that depends on algorithm, and weather prediction depends on the input. If we have accurate and more input, it will be accurate. Certainly, yes, with quantum computer, it may help, but I can't say relatively now, right? And over the year, even things on classical computing is also improving, right? So, yeah, but what will happen, the quantum computer, we will have various scenarios together. Right now, what we do is we run the various models and we try to make ensemble in weather forecast, and we do the forecasting. So sometimes we run them one by one, depending on the compute power and so on. In quantum computer, all scenarios will run in one go, and we will have better ensemble. Right? So in that way, accuracy will improve. That's right. QODA is open source. Yes, QODA is open source. What is QML? Quantum machine learning. So we have machine learning, and now we started this quantum machine learning. That is the thing. Today I am not elaborating more, but I will come back on that maybe in separate session. Right. Apart from, so this is from Prashant SAG. Apart from Q-state vector and tensor Q-quantum, have NVIDIA think about density metrics for noise simulation as well. Right now, I think the work is going on for density metrics. So our collaborators are working on that. We can, yeah. Can you please discuss the slide again? 3 applications were discussed: machine learning, protein folding. So those were the key upcoming area where the quantum computing being used. Or they are more focused there for this, all 3 algorithms. I think you are looking for this. So machine learning, protein building, and the last one is route optimization. So 3 sides, the main research work is going on. All 3 have their own challenges, and then new things are coming up in that direction. So for example, like for quantum machine learning, how to use the machine learning algorithms. There are debate also that we should use the classical machine learning input data, or we should have quantum related data which can be more understandable by quantum processor, or there are various things going on in that direction, right? So yeah, but these are the key 3 areas where the work is going on. You will find that research if you search online, you will find that. Can we link stochastic learning with quantum computing? I guess yes, that can be done, but required some work there. Yes. Able to compute data as fast as close to quantum. Hybrid computer be able to compute data as fast. So hybrid computer is doing that, the fast, but the quantum is different. What you say, thought process is different, qubits are different, then there's superposition, and they represent various scenarios together. So that way it can capture various scenarios in one go, depending on number of qubits, what it has, quantum computer. Whereas in classical computer or CPU plus GPU computer, where we are making things faster, but that remains the theory is on bits only, 0 or 1. Solely hardware, and will there be new high-level language program on? So ecosystem on quantum computers is being developed. There are various things already there. You should look for, the IBM has a good, what you say, well-documented web pages. You should look there. You will find the ecosystem there. All algorithms, various algorithms used in quantum, they are available there. You may get more details there. Yeah. I think the next question from Raj, I already answered. Will quantum computer finish the classical computer? No, both will go together. Hybrid will work. Is qubit like an analog state, since bit refers to a binary state? How does one perceive the state? Like, does the decision making changes with the new logic? Yes, the decision making changes with the new logic. Suppose one has the state with 40%, we say in one state, 60% another state, and how our program logic works, where we give the more weightage, accordingly the final results change, and that's how the decision making change. Same with the example, if we toss the coin, how the head or tail it comes. Last, the computer know only head wins. It will flip the coin towards head and it will go there. How does implementation strategy in data simulation of AI, machine learning, conjugative derive the inference analysis? Is it question about quantum, or I'm not getting Monali Roy? What do you mean by this question? Is it related to quantum or classical computing? I'm not getting that. Future, on which computer language we should focus? Python, Java, C++? Good question. I would say nowadays everything coming with the Python. So certainly Python will be used. And of course, C++ will be there for computation. Every language will be there. As I said, classical computer will be there. And it will work in hybrid mode with quantum and classical both. Now, quantum computing can work for ML, DL, both. Right now, more work is going on towards QML side, but slowly it will start with deep learning also. Yeah. Yes, there is a training also with the QML. Yes, they are there. Some research paper are there. Just look on the Google, you will find those. Or maybe I will have separate session on QML that I can do. It's a deep, vast field, right? So yeah. Since we can use multiple vectors represent state 0, 1, and the probability, is there a more info provided by qubits as compared to existing bits? Yeah, if you see one qubit represent 2 states, right? Again, I might be repeating the same thing, but one qubit represent 2 states. But if there are 2 qubits, they represent 4 states. So that's how 2 raised to power n states are being represented. So on classical computer, we have either state 0 and 1, and one bit is disconnect with another bit, right? They are totally separate. Whereas in the quantum side, with the superposition and entanglement, they are connected with each other. So yeah. What is the memory speed and latency? So let the quantum computer come and then we will talk more about memory speed and latency. But right now on simulator, which runs on classical computing, it's the same memory speed and latency what we have on classical computing, right? I'm currently master thesis on QML. I'm not a physicist. It's an AI master. I see my job is more on intersection between IT and business. Do you have any tips or connections on how to get into the industry? I think we will take this question separately. What is then David, what are the errors associated with quantum machine learning? I think again we are going deeper into the QML. There are I'm unsure about 2 kinds of error. One is quantum algorithm has its own error, it propagates. And you are talking about QML error. So is it error during training or that error from the quantum gates? But both type of errors are there. I can't quantify right now, but yes, errors are there. Yeah. Monali, which question was there for quantum computing? So are you guys using graphene for quantum computing since it has been discovered in Switzerland in order to build quantum computer? So I'm not aware about the graphene being used for quantum computers, or you're talking about quantum computing and computers. Okay. I'm unsure about this. NVIDIA, we do not have quantum computer. We are just providing a framework which accelerate the quantum simulating frameworks, right? We are not building quantum computers, right? Quantum and Boston augmentation with performance. Sorry, Monali, I am still not getting your questions. So sorry for that.
I will help you with that, sir. Actually, her question was the part you asked, right? How does implementation strategy and data simulation of AI and machine learning, conjugate equipment technology, derived strategy deployment, infringed, enhance the resistance of electronic equipment about working potential and consistently?
Okay.
It's just a few questions before.
Still sorry, I'm not getting it.
It's completely fine. Do you want me to copy and paste the question?
Yeah, please, whenever, maybe I will take later on, but I'm still not
Oh, no
getting,
problem.
please ask from me. I mean, that
Okay.
I'm not getting. Yeah.
Okay. Murali, you can surely get in touch with him later on, and you can continue the discussion. As we can see, the time is also up. So okay, perfect. So thank you so much, Dr. Manish. This session has been amazing. You can see the feedback from our attendees in the chat section itself. Everyone has loved it a lot. Thank you so much on the behalf of Analytics Vidya as well. So we hope that we have few more sessions with you ahead in the future also. And
Sure. Once again, maybe I might be a little fast, but it's a vast field, as well as understanding between bits and qubits is confusing, and it will come slowly. Yeah.
mhm, yes,
But thanks a
surely.
lot for giving me this opportunity to discuss with all of you. Thanks again. Yeah.
Pleasure is all ours. Thank you so much, sir, and thank you for everyone to participate and be so patient. Thanks a lot, and I hope you all have a great evening ahead. Thank you so much.
Thank you. Thanks, everyone.